This video is on decision trees with Rattle part 1 of 2. Today we're going to see how to save a project and how to open up a project in Rattle. Just reviewing that. Variables to exclude. We're going to transform a variable. We're going to create a tree, and we will then transfer the tree rules into a format better for analyzing, and we will be looking at the financial implication. To save a project or how to open up a project. So here is where we would open up a file. However, to open up a project after we've saved it, we're going to go to open. We're going to find my project. It's right over here. This is it. And open. Wait a little bit and it's going to populate. So here we have our project. Same manner, to save it, you just go project, save as, and you can save it wherever you'd like. Cancel here. You don't need to waste time. So, first thing that I'd like you to do is to variables to exclude. So one thing is the event ID. I'm going to ignore this variable. Again, it's just that there's just way too many values, and the nature of the event ID doesn't really lend itself very good for modeling. Therefore, we are going to go down here and we're going to make sure that converter is our target, that sales channel, we're ignoring that. And we're also going to be ignoring converter telesales, okay? Because it's a little bit redundant with converter and sales channel. If there is no sales channel, it wasn't a sale. Therefore, it's going to be very misleading to use the converter, because obviously wherever sales channel is missing, you have a 0 for a converter. Wherever sales channel is populated, we have a converter. So now, other thing we're going to do is that we have a lot of data. We have over 100,000 records. So I'm just going to use 10% of my data for creating the model. I'm going to use 20% for the validation, and I'm going to use 70% for testing. Basically what I want to do is just create the model with just 10% of the data. I'm going to hit execute here. Never forget to do that. And we're all set. So the next thing we're going to do is that we're going to transform a variable. The reason why we're going to transform a variable, although classification and regression trees, they can handle, they're not a requirement to have normalized data, it still is a good practice. So let's just take any data that we know that is extremely skewed. And again, data that we know that is extremely skewed is most likely is going to be one of the first your home value. So we have a mean of 204, missing a few there. Okay, not too much information, so I'm going to go better to 6, and I'm going to hit execute. Doesn't tell me if it's normally distributed or not yet. Okay, so here we have age and site, mean and median very close together. We have skewness and kurtosis pretty much in line, so that's pretty good, well normally distributed. So home value insight has a mean of 204 and a median of 167. Now that's the first indicator that it's not normally distributed. Now it's positively skewed, and it's very, very peaked. You have the kurtosis. So let's go ahead and try to transform it. And in case you still are not sure, we can always go to distribution and we can do a histogram and hit execute. And here we see an extremely skewed variable. So to transform this variable, and other algorithms will require this, is that we're going to do a natural log. Okay, and we're going to do the natural log of home value insight. And hit execute. And now we're going to explore to see this new variable of ours. Well, first of all, here in the data, we can now see that it is created RGL, recoded log home value insight. Okay, great. And the original home value insight, which is right over here, automatically is set to ignore. Now we're going to go here to explore, and we're going to ask now for summary statistics, and we did like the basics. So let's hit execute again, just so we can have our new variable. Go all the way down, and here, this is the recoded log home value insight. We have a mean of 5.18, median 5.11, looking good, and skewness and kurtosis are also looking pretty good here. So again, not exactly necessary for classification of regression trees. However, it is a good practice because those extreme values can create some abnormal or strange splits. So let's go here to model, and I'm just going to hit, here we have checked off tree. We have a traditional tree, minimum split 20, minimum bucket is 7 observation, maximum depth 30, complexity 0.01. We can go over a little bit more detail next class on those values, but for right now we're just going to hit the execute button. And here we have our tree. This is telling us a lot of information on the tree. However, it's a little bit difficult to interpret. We can always draw it. Asking us for so let's hit install now. For now, let's let this install. But what we want to do is, again, once we see this, we can see our model right over here. I'm sorry, I hit it twice, so we're seeing it twice. So here we see our model, and again, it's split very nice. We have all the inputs. Now what we're going to do is we are going to take a look at what this output means for us. So to better interpret this, I like to just highlight this, hit copy, and we're going to create a nice looking tree that we can use information to interpret. So now that we've created our tree, we want to put this information in a more useful format, something that helps us interpret the results. So here I have the first line from the result of the tree, and I'm just going to plug that in the top node. As you see, I'm just organizing the data, and probably in a way that's going to be easier for all of us to see. So 15,490, that's the total sample population here. And I just put that right over there. You have a conversion rate, 0.0338. In other words, conversion rate of 3.38%. Percent of population, given that it's the top node, it's 100%. Cost per converter is the cost per lead divided by conversion rate. The cost per lead is constant, or we're assuming it to be constant in this endeavor. So that gives us 8 divided by 0.0338 gives us 236. We proceed with the next split, which is risk insight, or actually the first split. So in this first split, we have risk insight less than 67.5. I actually rounded it off to 68. Now, here we have an N population within this cell of 8,715. And we also have a conversion rate of 0.022. Conversion rate 0.022. Percent of population, 56%. I did 8,715 divided by 15,490. So the population in this node divided by the sample population. Cost per converter, I took $8 divided by 2.22, and it gave me 385. Now the next line right over here is over here. So risk insight greater than or equal to 68. Again, I rounded it. Probably you should not. Now, N, 6,514. 6,514. Conversion rate, 4.98. 4.98. Percent of population. You take 6,514, which is what belongs here in this node, divided by 15,490, gives you 44%. Or you can do as I did, take 100%, subtract the other side, which is 56, you'll get 44. Cost per converter, 160. How did I get that? $8 divided by 4.98 will give you 160. And we keep on doing that for all the other lines here, all the other splits. And you start filling in your tree and it gets bigger and bigger. But what we want to see, and you can do this on your own, but we want to see here is really what implication does this have on the business. So we started out at cost per converter, cost per sale of $236. And now in our first split, we're able to achieve 160. That's quite a discount by taking the top 44% of the population. And we determine which is the top or the cream of the crop by just saying wherever risk insight is greater than 68. So what are the implications for the business? The cost per converter is reduced by 32% by using the top 44% of the leads. And this is the type of analytics that is expected when you're doing these type of analyses. We don't want to just throw out a formula. We want to say what are the implications for the business.